Okay, hi everyone. So it's going to be lecture 32. So this is, I guess, a slight change in the path from talking about class groups. We'll return to that shortly, but I'm going to talk a little bit about um, how ideals factor in extensions. So um, basically, what do I mean by this? We know that ideals in Dedekind domains factor uniquely as products of prime ideals. Um, and one of the big questions in algebraic number theory, I guess, is we're trying to study number fields. And so we're trying to study rings of integers in those number fields. Um, and one way to do this is to study how ideals in a smaller ring of integers change when you go to a larger ring of integers. So what do I mean by this? So here's kind of one of the broad questions that we're going to try to answer in the next couple of lectures. So given an extension of Dedekind domains, and let's say an ideal A in my first Dedekind domain A, how does A times B factor into a product of primes? So the ideal generated by A in my bigger ring B. Okay. This is the question I want to try to answer in the next few lectures. And typically, rather than just taking an arbitrary ideal, basically you can figure out what happens to an arbitrary ideal by looking at prime ideals. So we're going to look specifically at the case where A is a prime ideal. So the first part of this is going to be, we're going to talk about some notation and definitions so that we can have some vocabulary to talk about these concepts. Notation. We're going to state the main theorem, which is something called the EFG theorem. It tells us a lot about how primes factor in larger ideals. Okay, and the goal of the next two lectures, like this one and the next one, are going to be to prove this theorem. But the proof is a little technical, so it's going to take some time. We're going to prove a lemma, basically that the Galois group so I have a Galois extension of number fields, and A and B are rings of integers in those number fields. Then the Galois group with these number fields are going to act transitively on a given prime ideal. What do I want to say? On the primes over a given Okay. And again, I'll clarify the statement. Like, what does this phrase "primes over a given prime" mean, and stuff like this. But basically, the gist is that the Galois group act transitively on some set of primes. And then the last thing is we'll prove another lemma, which allows us to compute some relevant numbers. In a useful way. So yeah, that was a really vague statement. And again, I'll clarify this notation. But this is going to be this lemma will be important in the proof of the EFG theorem. And this F is going to be something called the residue degree, and E is going to be called the ramification degree, and it appears here as well. Okay. So first, let's go ahead and get started with some notation. So I'm going to start, I guess, maybe just like some general notation of how we actually write things down. So for the following, I'm going to let A contained in B be Dedekind domains. And I'm going to let P contained in A be a prime ideal. And the ideal P generates in B is going to factor into some product of primes. Let's say PB is equal to, and then I've got these big math frac P's. P1 to the E1, PG to the EG. Okay. So this is become aware. Basically, these guys are distinct primes. And the EIs are integers. I guess they're not negative integers, or positive integers. Okay. So I've got this factorization. These EIs are going to be called the residue degrees, or not the residue degrees, the ramification degrees. And then we'll define the residue degrees as well. So 32.1 definition. Okay. If any EI is greater than 1, we say that the prime ideal P is ramified in B. Okay. Each of these big PIs is called a prime lying over P, or a prime over P. Okay. Alternatively, we'll just say that these PIs divides little p. Okay. Because basically one of these PIs divides the ideal p generates in B. Okay. And the number EI is called the ramification index. Of PI over P. Okay. Sometimes we'll denote this by just E of E of PI over P. Okay, so these are all the concepts associated with ramification. So these are basically the powers of the primes that appear. And then there's another set of definitions which are basically going to be associated to residue degrees. First, let me make a following remark. Which is that the prime B and B lies over a little prime P and A if and only if P intersect A is little p. Okay. The way you check this is basically, so one direction is like, let's say P lies over little p. Well, then big P certainly contains little p in that case, and big P intersect, I guess little p is also a subset of A. So this thing contains little p, so maybe I should just write this down. Yeah. If P, let's say, divides P, and that means that this is true. So and you can quickly see that this contains little p. Since basically this is going to be a proper, it's going to be a prime ideal. And you can check this just from the definition. It's going to be proper because it doesn't contain 1. But since this thing is prime, actually I don't even need that. All I need is that this is proper and P is maximal as A is a Dedekind domain. So we have equality in this case. And then the other way around follows from the previous proposition we proved last time about containment being equivalent to division. So if B intersect A equals P, and this should not be B, C. Yeah, these P's look too close to B's. Okay. If big P intersect A equals little p, then this is going to be contained in big P. So by, this is 31.2. This guy divides B. Okay. So this concept of lying over is really just saying that big P intersect little a is equal to little p. Okay, now we're going to define the notions of residue degree. So 32.3. That's another definition. So we're going to define the residue class degree of, say, big P over little p by, so it's denoted F instead of E. The residue class degree of big P over little p is the degree of the following field extension. Okay. So you can check that basically A mod P is going to be a subfield of B mod P, and the residue degree is the degree of that field extension. Okay. Okay, and then there's some concepts of special behavior of these guys. Okay. So we're going to let Fi be the residue degree of the ith prime. And a prime is said to split completely if all the EIs and the FIs are equal to 1. Okay. And a prime is said to be inert if the EIs are all equal to 1, and so is G, the number of distinct primes. Basically, this means, this concept of inert means that PB is prime. Okay. So basically, your prime ideals are going to split into some product of primes in B. We say that they're ramified if one of these powers is bigger than 1. We say it's split completely if all the powers are 1 and all the residue degrees are 1. And we say it's inert if there's basically only one prime here. Yeah. Okay, so that's kind of the vocabulary we've got. And the main theorem, so let me go ahead and state the theorem, which is called the EFG theorem. and we're not going to prove it today, but we're going to start working on the lemmas that go into the proof. So the theorem goes like this. So we're going to let L over K be a field extension I would say of degree m. Let's say, well, really the way I want to write this is like this. Really I want to start with the Dedekind domains. So I'm going to let A contained in B be Dedekind domains. And I'm going to let K be the fraction field of A. L be the fraction field of B. And I'm going to suppose that the degree of L over K is M. Okay. I'm going to let P be in A, B prime. And let's say we know that PB factors in the following way, as above, P1 to the E1, PG to the EG. If Fi and Ei have the same notation as above, so the residue degrees and the ramification index, then basically there's this following constraint on these residue degrees, which is that the sum of all the products of these guys has to be equal to the degree of these fields M. Okay, and we can say something stronger in the Galois case. If L over K is Galois, then all the EIs are equal. All ramification indices are equal. And all the residue degrees are equal. And we get basically this formula here turns into E times F times G equals M, where E is the common value of all the residue degrees, or E is the common value of all the ramification indices, and F is the common value of all the residue degrees. Okay, and so this is why it's called the EFG theorem. It gives us this relationship between the E's, the F's, and the G's. Okay, so the goal of the next two lectures is to provide a proof of this theorem. We're going to need a couple of different lemmas before we can sit down and actually prove this thing. The first is to understand, I guess, yeah, first we'll think about the Galois case, because there's a useful lemma that actually ends up being useful more generally. And then we'll think about this case, and we'll think about basically what one of these single pairs looks like. Okay. So, proposition. $32.6. We're going gonna let A, B, L, and K be as above. And we're gonna assume also that L over K is Galois. So we're going to let P be a prime in A. And we're going to let S be the set of primes in B lying over little p. Okay, and then basically we have this action of the Galois group on S. And it's not just any action. In particular, this action is transitive. So finds a transitive action. And this action, again, will be useful later in the course. But it's going to be first useful for proving this theorem. In particular, this fact that all the ramification and residue degrees are equal. Defines a transitive action. Let's say on S. Okay. So let's go ahead and prove this guy. So first we'll prove that the action is well defined. So we're going to let sigma be in the Galois group. And let's say I've got a prime B in S. So one can pretty easily check just using the definition of prime ideals and the fact that sigma is like a field isomorphism, or like a isomorphism of rings from yeah, I need to know so there's a slight issue with the way I've defined things here. Which is that I need to know that sigma preserves B and A. Which is probably not true for general Dedekind domains sitting inside these fields. So really, here I want so the main application of this is going to be in this setting where A and B are the rings of integers in number fields L and K, right? So in that setting, we don't run into any issues because the Galois group certainly preserves the ring of integers. So let's just make a slight change to these things. So yeah, let's just state this for number fields for now. Okay, that was exciting. Okay, so yeah, let's just state this for number fields for now. We'll worry about what generalizations we can do later. So K be number fields, with rings of integers say b and a respectively. Okay, so now this will work. And sigma of beta contained in B will be a prime ideal. Okay, it's not too hard to check. And since sigma fixes A, then sigma of B intersect A basically that sigma of B will still lie over P. Okay. Okay. Yeah, I guess maybe I also need that sigma is injected in here in order to make this statement. Okay, regardless, this gives a well-defined action of the Galois group on S. The kind of difficult part is to show that this action is transitive. Okay. So I'm gonna let, let's say, B1 and B2 B primes over the same prime little p. And suppose, for the sake of contradiction, that no sigma takes B1 to B2. Okay. So this tells me that the collection basically of all sigma of beta sub 1s, or all sigmas of P1s, these are a family of like distinct primes from P2. By the Chinese remainder theorem, or by Sun's theorem, I can find an element beta with the following congruence conditions. Beta is equivalent to 0. Beta should be in B. Beta is equivalent to 0 mod beta 2, and it's equivalent to 1 modulo sigma beta 1 for all sigma. Okay. So basically, one way to interpret Sun's theorem is I can solve like any family of congruences modulo distinct prime powers. Okay. And so that's what I'm doing here, is finding a beta that does this. What does this tell me? For this beta, beta is going to be in the second prime ideal, but not in any of the sigma of beta 1s. And this is for all sigma in the Galois group. Okay. Then take little b to be the norm of this beta in A. Okay, this is the product over all the Galois conjugates of beta. Okay, so this is going to lie in A because it's the norm of an element in B, but also it's going to lie in the prime ideal B2 because, well, beta lies in B2 and this thing's an ideal. And since B2 lies over little p, this is going to be in P. Now, since B1 also divides P, B is also going to be in P1. Thus, since B1 is prime, I've got the, if I view B as the product of these Galois conjugates, I see that one of the Galois conjugates has to lie in one of the Galois conjugates has to lie in B1. But then we're going to get a contradiction. Because then beta will lie in sigma inverse of B1, which is a contradiction by this guy. Okay. Hence, there has to be some sigma which takes B1 to B2. So basically, the Galois group in this setting acts transitively on these prime ideals over a given prime ideal. And this is going to be useful to show that the ramification indices and the residue degrees are all equal in the Galois setting. Okay. So the next lemma I want to prove is that it's basically a way of computing one of these single f times e's, which is going to be useful in the proof of the EFG theorem. So this will be a lemma 32.7. So I'm going to let A, B, L, and K be as above. So again, we're going to assume for now that L and K are number fields and A and B are the ring of integers in those guys. A is in K and B is in L. And that the extension is of degree M. So I'm going to let beta be prime of B over P prime of A. And not, I always keep calling these things betas, but really they should be P's. P be prime of B over P prime of A. Then I'm just going to call F the residue degree of this guy. And E the ramification index. If this is the case, then E times F is going to be the degree of B modulo P to the E over A mod P. Okay. So basically we're going to be able to understand a single term in the sum above, which will help us understand the entire sum. Proof. Basically, you look at the following chain. Start with B, then you look at 1 power of P, then you look at 2 powers of P, all the way down to E powers of P. And you want to look at an arbitrary quotient. So basically we're going to compute the dimension of the whole quotient by computing the dimension of each subquotient. So I can view this as a B mod P vector space. And so I'm going to understand this as a B mod P vector space, which is then going to allow me to understand it as an A mod P vector space. Okay. And a subspace of this guy will correspond to an ideal. In between these two guys. Okay, so you can think about this from the perspective of the correspondence theorem. Basically, considering this as a B mod P vector space is more or less the same thing as considering this as a B module, if you like. And then B modules here correspond to B modules in between these two guys by the correspondence theorem, and B modules are the same thing as ideals. However, there's only basically 2 ideals between these two guys. There's the top one and the bottom one. By unique factorization, of ideals, and this might be overkill, but it certainly does the job, because if I is contained in B to the R, then B to the R divides I, and if I contains B to the R plus 1, then I divides B to the R plus 1, and there's only 2 choices then. And every time, yeah, maybe I should choose different notation. By unique factorization of ideals, I is this guy, or I is P to the R plus 1. What does this tell us? It tells us that there are only 2 subspaces of this guy. There's a 0 subspace corresponding to this ideal, or there's only 2 subspaces of this guy. There's a 0 subspace corresponding to this one, or the whole space corresponding to this one. if there are only two subspaces, then this is one-dimensional. As a B mod P vector space. Okay. If it's one-dimensional as a B mod P vector space, then in particular we have an isomorphism. Yeah, maybe in particular is the wrong word. This guy's going to be isomorphic as B mod P vector spaces. As both P mod B vector spaces, B mod P vector spaces, but also as A mod P vector spaces, so that whatever isomorphism you write down here is also going to be an A mod P vector space isomorphism. Okay. That's basically just because A is contained in B, and P acts trivially on these things. Okay. Each quotient in this chain, this guy has dimension F as an A mod P vector space. So each quotient in this chain has dimension F. And then you need to do a little bit of linear algebra. Basically using the following two things, you can get the result. That the dimension of a quotient space, basically you just subtract the dimension off the dimension of the subspace. And I think it's like the second isomorphism theorem. B mod P to the R mod B mod P to the R plus 1 is isomorphic to B to the R mod B to the R plus 1. Using these two facts, kind of stitching them together, gives the desired result. That the degree of the whole quotient dimension of this vector space is equal to E times F. Okay. So that's the proof of this lemma, and it basically allows us to understand a single piece of this sum. And then using that, we'll be able to understand the whole sum a little bit better and prove the theorem. So next time we'll basically prove the theorem, and then we'll also prove the special case using this lemma we proved about the Galois group acting transitively.